Everyone seems very serious today. Should be joyous. It's our penultimate class. I guess we've got this class and Thursdays. That's it. You're off on your lonesome after that. Okay. Should we get going? Okay. All right. So as we made the point last time, when you stand on a field with no idea what's under your feet, you need that information to be able to go ahead. We can divide it up into two parts. One is what we might call direct investigation, where you dig a hole or drill a hole, and then with that hole, you want to do something with it. You want to recover samples. So far we've really only talked about drilling the hole part. And we know that if you want to drill in soil, you can use either augers or rotary drilling to advance. If you want to drill in rock, you can use rotary drilling or diamond drilling to advance. And we talked about the pitfalls, I guess, the advantages and pitfalls of each of those last time. And so today we'll perhaps finish some of that stuff off. I discovered that you like to look at pictures last time. So maybe we'll try some of that again today. It's planned anyway. And then in addition to what we talked about last time and continuing this time, we'll talk about how to sample. We sample differently for soil and rock with different instruments. If you've gone to the cost of drilling a hole for $20 a foot, you might want to do something with it. And so often you either put piezometers in it to measure water levels, water table, or you use packers to isolate different zones within the borehole so you can recover perhaps water quality samples. And we'll also talk a little bit about so-called continuous profiling, sometimes called direct push, because you just physically push a penetrator into the ground and go from there. So that's it. Let's finish up from what we talked about last time. We were messing around with some different locations, talked about augers and rotary drilling for soil, rotary drilling and diamond drilling for rock. This is a hollow stem rig with a hollow stem auger with its tip right here and soil on the flights. This rotary connection here that lifts the whole material up into the mast. It's a piezometer that's been put in and has been left right next door to it. And the rig has been taken slightly off hole by 5 feet or so. And during advance, it's held, there's a capstone here that grabs it, turns it. There's a universal joint that allows it to go at different angles slightly. It has a hollow stem inside this tube, so you can actually recover the thin piece of drill rod out of the middle so that it leaves the casing in the ground and you can advance tools, which we'll talk about today, to where the drill bit is and then sample from there. The same rig again, just from a different angle. We did talk about rotary drilling. This is where the drilling mud goes. This is where the drill hole is. So you drill down through here. The return water gets dumped into this bathtub, basically. And this bathtub has a grill which acts as a filter to take out the big cuttings, and then the return fluid to suck it up and pump it back down the hole again is in this portion here. Tricone bit, yeah, just as we said. 3 cones on a spindle. It doesn't cut and it's not driven. It just is rotated by the rotation of the drill steel on the bottom of the hole. And as a result of this, these runners just run over the bottom of the hole. And there's enough force on each of these little teeth that they break off portions of the hole. And then the water, it's upside down, of course. The water's, actually, can they do that? Oh, yeah. The water comes down, the drill fluid comes down the drill pipe out of the bit, washes away the cuttings, and then returns it back on the other side. Good. Another rig, similar, actually near Jasper as well. The central Canadian Rockies, or the foothills. This is a rig that's mounted on a Nodwell for getting around on bad land, poor terrain, I guess. A water truck, drill steel. The mast is raised. It would go down flat on top of this roof otherwise. A piece of drill rod in here with water, drill fluid being circulated up into here and then down into the drill bit for it to go through. Again, this is where the drill steel would go. This chain is to physically pull weight down, the weight of the truck, I guess, against the drill bit to be able to advance it by rotating it in the bottom of the hole. This looks like the return tube that would take the water out of this, the drill fluid out of this end of the return tub and pass it up the mast and then down into the drill bit. Another rig ready to go. This is the bath that has the drilling fluid catcher in it, as you've seen. And again, actually here it is, right? This is the drill bath. This is the pipe that's supplying the drill fluid up the mast to go down the drill tube, hollow drill tube, into the bottom of the hole and back to circulate up here. So it's all very straightforward. If you don't have to drill with water, and you can get a bay with drilling with air, flush, or with foam, it's much easier because you don't have to resupply a water truck to be able to pump it down the hole. You never get 100% return, so you have to bring another truckload of water in to continue. This is the drill steel here, has slightly larger flanges on the end so it can go into the next male thread that gets put on there. And same idea, but actually in an underground research lab where it's almost an office environment. So what they've got here is to avoid dust going into this kind of office-like workspace. It's an underground research lab for geoscience. Is that this is a vacuum that's taking all the dust away and disposing of it through a filter. Same idea. This is 2 rails with a rotating head on it. Drill steel goes into the borehole, is turned and advances, and as it advances, it drops down. This is run, there's no liquid going into this. This is just a hydraulic power powering this rotating turntable. Don't know what that is. The best core you'll ever see, a rotary rig. So the rigs we looked at just now were all for use with tricone bits. And so they destroy the core as you make it, because obviously there's no core that can advance up inside the bit because it's closed. And so if you look at rotary coring or diamond drill coring, same idea, a mast, drill steel which goes into the mast. Can't see it so well here. It's in China. It's in the Gobi Desert, actually. It's the site of the Chinese experimental radioactive waste repository. The drill steel gets lifted up into the mast and gets turned as it gets pushed into the ground. A place called Beishan. Bei, I think, means Beijing is north capital, so Bei is north, and Tianshan is mountain, so North Mountain. Bless you. A mud pit for the drilling fluid. It's the desert, Gobi Desert, so it's lined and it's all that water will be brought in. And actually, the most amazing core you could ever imagine. Core usually comes out like this. We talked about core barrels where you have like a cookie cutter with artificial diamonds placed around it to abrade the rock, and then the rock rises in the tube as the tube advances into the ground. And because there's a drag on the side of the core as it goes into it, it gets twisted off. So any natural fractures there will typically get twisted off just by the torque of the material. And only if you have really fantastic rock. This is a granite, nice big potassium feldspar crystals in the quartz. Typically it would look like this. You take it out of the core barrel, you put it into a core box. You saw some other core boxes in Sweden last time, I think, and it would typically be broken up, mainly with natural fractures providing natural planes where the core will break. But if you're lucky, in a place where you want to store radioactive waste, you have stuff that's so competent. These are 10-foot sections of core, and it's supported only at the ends, and it's absolutely intact. Quite amazing. And this is the same idea. These are 2 core barrels here inside some casing, just used as an impromptu furrow, I guess, to be able to break the core out of the core barrels and then put it in those boxes and log it. Camel in the Gobi Desert, core boxes. And actually the object of all this drilling is an experimental site for to do experiments with heaters to simulate hot radioactive waste and what it does to the hydrogeology of a site. And so as part of this experimental program, where this core comes from, they excavated a 2.5-kilometer tunnel in a spiral to get to 500 meters, 1,500 feet below the surface. And there they'll have a bunch of experiments to look at the hydrogeology of the site. The hydrogeology of the site, judging from this core, is pretty tight. Super low permeabilities, which is perhaps what you want if you want to contain the wastes. Northwest Territories again, Mackenzie River. You can see on here, this is a solid stem auger with all the muck pulled on it. It's being taken up in the mast and out of the hole, and obviously takes no sample in that particular case. This is kind of in the springtime. This is probably March. The cover is for bad weather, cold weather. This is just a tower to be able to lift tools up and drill. It could also be used, as it turns out, for rotary drilling, diamond drilling. Weather not always great. Solid stem auger again, clipped onto the next one up here, just bringing material up on the flights. The other flights right here with a male coupling and a female coupling at the bottom that are joined and then has a clip put to keep it in one place. You lift the drill steel up into the mast by using this capstan and a rope. A different sampling tool. This is actually a permafrost barrel. We don't really need to deal with that here, but with the soil on it. And I guess that's what we'll finish with here. So in being able to advance these holes, those are the kind of different methods that we can perhaps use. And so if we end up with a hole developed for any of these methods, what we might like to do is take some samples. If we have diamond drilling, which would be this, we don't need to take any samples because the very act of advancing gives us an actual sample inside the tool, which is then raised to the surface, either by pulling all the drill steel up to the surface and breaking it open, or preferably bringing the core tube, which is present right at the base, up through the remaining line up to the surface, breaking it open, taking the core out, and while you're doing that, putting the other core barrel down and then just keeping on drilling while you're breaking the other stuff open. And so if you're doing diamond coring, you naturally get the sample in the core barrel and bring it up to the surface. If you're not diamond drilling, then the typical tools that you have fall into one of two categories. If you're drilling in silts and clays, very soft sediments, you'll use what I guess is generically called a thin-walled sampler. And I guess the idea is if you're at the bottom of the hole, like this, and you have a sampler which is nice and sharp. So if you imagine this as being, we'll see some in a minute, a piece of brass tube maybe 4 inches in diameter, maybe with less than 1/10 of an inch wall thickness. When you push this physically into the ground at the bottom of the borehole, just pushing it, then what it will do is like a cookie cutter. It'll go in, maybe they're usually about 18 inches long. You'll push it down the full length just by pushing it, twist it to break it off at the top, and then pull out the whole sample. That's one way of sampling. So if you're in clay, I guess, on this side, if you're on sands and gravels, then you'll use a thick wall sampler. Same deal. You have the bottom of the borehole, but now because this gravel is much more resistant, you can't push it in anymore. You have to bang it into the ground. So it'd be the same idea, but it wouldn't be a thin wall sampler. It would be something with a thick walls to it, perhaps not quite 1/2 inch, but maybe 1/4 inch in thickness, and it's physically just banged into the ground to advance it. And it would look a bit like this. And then once you get down a foot, probably not 18, it might be 18 inches, then you've counted all the number of blows you have to advance it. So that's one metric you have as to what the density of the material is. But you also have a sample that's gone up inside it and you can retrieve. And the difference between these things is that this is kind of minimum disturbance because it's such a thin wall, and a thin wall, and it's physically slowly pushed into the ground to be able to tick it off and pull it up. And this is beaten into the ground and has a thick wall into it. And so you could imagine the material that's right under this wall kind of gets squeezed in here and changes the density here, and it's a disturbed sample. So disturbed sample, undisturbed, nominally undisturbed sample. So those are the two main divisions. One is banged into the ground. So this, you could imagine, is a tube. It's called a split spoon because it has a cutting shoe on it. This portion is a cylindrical portion that is threaded at both ends and breaks in two, hence a split barrel. And so you put the two together, you screw it into this upper coupling, and then you screw a shoe onto the bottom. You have a check ball bearing valve which allows water to flow only one way, up here. So you put it into the ground, you put it to the bottom of the hole, then you physically bang it in. You bang it in until the soil comes all the way up here. And then once you've gotten that full penetration, you pull it out. The reason you have a check valve in here because the column will be filled with water. And if you don't have a check valve in, the water will be under pressure. It'll just wash the sample straight out. You take it up onto the surface. You uncouple it at the top. You take off the shoe at the bottom. You open it. It's a disturbed sample. Typically, you'd bag it and keep it to be able to see what the gradation is. So for granular samples, sands and gravels, you'd use that. A thin-walled sampler is physically just put on the bottom, as I mentioned, and pushed in. They come in a variety of ways. This specifically is a piston sampler. And so the idea here is that this is what's advanced to the base of the hole. And then this piston in here sits on the bottom of the hole while the tube around it physically goes further ahead of the hole. And so the idea here is not so much in clays, but in silts. This plunger, it's like a syringe, is right in the bottom of the hole. And so now when you twist it to break it off at the bottom and then retract it, if you don't have something that can provide suction at this interface here, so it pulls the sample back out, it also will just wash out. You don't need a check valve as you do for sand, which would wash out, because this wouldn't wash out. But if you don't have something to suck it up, then it will tend to stay in the ground and just allow the tube to come up empty. So two kinds, thin wall samplers, thick wall samplers, sometimes with fancy things like a piston in it to be able to make sure that you get recovery. I guess this is a thin wall sampler. You can see the difference between the thickness of this wall and this wall. And this is just a piece of like plumbing, when they used to plumb houses with a brass tube, but probably 4 inches in diameter. And this one has a check valve so that if you have things, so if it's a soft, granular sediment, it doesn't get washed out by the water pushing it out. Different varieties, all the same things. Again, another split spoon. I guess it kind of repeats itself. Different, maybe different weights to do different jobs. Don't know what that is. A bit of verbiage. Yeah, okay, you can see perhaps better here. This is, this is a split spoon. So a shoe on the bottom that screws in, coupling at the top, a thick wall tube that splits into two. It's threaded top and bottom, advanced down the hole, and then banged in, and a thin wall sampler where this wall here is much thinner than the stuff on the side. So where do we have? Don't know. Okay, let's have a look. See what we got. This is exactly that. All right. So this is the coupling that goes down to the end of the tube. So this is the piston that would go in advance of the tube. Oops. So if you can imagine this being the drill rod, this is this Shelby tube, so-called, or thin wall sampler. It fits on this coupling by being pushed up here, enveloping this, and then it's slightly larger than the internal diameter, slightly larger than the diameter of this. Yeah, and you can see it. So it fits over this. These little set screws get turned until they're flush with this casing. The Shelby tube goes up over it and has little holes, maybe at 90-degree increments around the circumference. And then once it's on here, you just pull these set screws out by advancing them up into this kind of position, and it locks that tube onto here. It's sitting here, it's open off to this side, I guess. And it's maybe 18 inches long. You can push this syringe, if you like, down all the way to the end, which is what it's like here. This is the coupling where it attaches on the tube. The piston's advanced all the way in. You put it on the gantry, lower it down the hole, put it on the base of the hole, and then with the weight of the drill rig, you push it the 18 inches or so into the ground. As it goes into the ground, this piston comes up level with the base of the borehole, so there's no air gap between the clay that's kind of advancing inside this, but it's not advancing inside it. It's the actual tube that's going down over it. And then when you pull it up, you keep the vacuum on it because there's no airspace, and bring it up to the surface. So all this contraption is taken off. It's advanced down this empty hole. Actually, you can see this is the same as before. This is the return drilling fluid. This is the drilling fluid being taken out of the tank and being passed up into the gantry and then going back down. A bunch of people mulling over exactly what to do with the Shelby tube. This is exactly what it looks like. This is an open one attached onto the component. Yeah, this is the business end. Piston, you can see some seals here. These are the set screws that come out. Looks like someone's hitting it with a hammer. Yeah, so lots of pictures. So I guess this just has a set screw. Maybe has it 120 degrees, I'm not sure. I only see one here. I don't see one there. With the piston down at the bottom. With a sample in it. So this is the coupling taken off. This is the now filled tube filled with soil with the coupling up here. This is a Tor vane. I don't know if I've got a better picture. Sometimes you want to measure the strength of soils. And one way to do it is to use a Tor vane. It's just a little spring held, I do have a picture somewhere, I thought. That's the impression. Yeah, okay. So you have this little ratchet here. These little fins get pushed into the end of the sample. It's on a spring, so not to compress it, a spring which acts as a torque wrench. And so you turn it, and as soon as it reaches a particular torque, this will fail, and it will record that torque magnitude on the scale here, and it gives you an impromptu strength of the soil if you need that. Not really for the things we're talking about, but you do for foundation engineering stuff. This is the coupling of the Shelby tube on top of the component. So this is the tube as it comes out. This is measuring its strength on the end after it's come out. This is the package. This is a tiger torch melting some wax. This is pouring the wax into the top because you want to preserve its nice pristine conditions, same water content, moisture content. And then caps put on the top of it to preserve it. So, yeah. Don't spill it on your hands. So, see the same things. Okay, that's it. I don't have any pictures of split spoons. Actually, while we're here, why don't I do that? It's maybe 12. Your eyes are probably better than mine. Are you 12 minutes yet? Close enough.
Yeah, right? And they're also recording pressures in two filters, two testers. We're just trying to see what the response is.
We don't need that. Yeah, so in live action. So you see all the components there. So this is advancing. This is the return fluid that has come down here, gone to the bottom, and be squirted back out. I'm not sure where the return fluid is going to. This is adding another rod. Usually they're much longer than that. They go up into the mast. But you saw, maybe you didn't see, as you go into here, this thread here is tapered, a male thread going into the other end of it. Usually it's not quite as light as that, usually heavy enough and long enough you have to pull them up into the mast. You screw it onto the pipe that's below it. And then zoom out perhaps. Then you attach inject the drilling fluid, goes down here, goes down to the bit. It's a rotary bit in this particular case, down to the bottom of the hole. Then it comes back around the outside of this tube. Yes. Don't feel the need to shout over myself. And so you see the string here to be able to seal the relatively loose threaded joint, and just advance to go further down. Doesn't like to do it in fast forward when it's on the screen. Doesn't like to show it. I don't lie. Pretty rudimentary. Does the job though. You see it's moist downstream of it and it's quite dry above it. This is pulling something out. Yeah. Just lifting it on a winch. Not sure what that's. A bit, tricone bit, small bit, a little bit. There you go. So you see the three cones, which are on spindles. They're not driven, but they merely rotate the bottom. This is drilling through clay. This never went into rock, so it's just a mess. Some December near Boston. There you go. I don't know, it showed the... I think this was actually a Shelby tube rather than, not the previous sample we showed, but this is putting a sampler into the hole. So it's flush level with the bottom of the hole. Hide Yasuhara, now professor at Kyoto University, taking a picture of something. So then this hammer being put on top of what's in the hole and then lifted a certain amount, has a certain weight. You lift it by just tightening the capstan here. As soon as it gets tightened, it lifts, and then you take it up to the top of its stroke and drop it down. You dutifully count how many blows it takes to go 6 inches, then a foot, then 18 inches, and record it. And then once it's gone the full 18 inches, you stop doing it, and you take the hammer off, you put it on the side, you couple the drill pipe to it, and then you start winching the drill pipe up into the mast, break it at the bottom, then take the next one up into the mast, depending on how far down the hole you are. So that's it. You only have to do it once, or 1 day's worth, and you know exactly what to do on all of these things. Yeah. That would be breaking pipe, I think. No, perhaps tightening it. No, setting it up. Sure, okay. Okay, it's a thin-walled sampler with the set screws at the top on the piston assembly, either going down the hole or coming in. Looks like going down the hole, perhaps. Maybe. Yeah, get some lay of the land. It's under an underpass, as I recall. Measuring it so you get it to the right depth where you know it's sitting at the bottom of the hole, and then how far you have to push it. A lot of deliberations going on. Unfreezing lines. So this is December. And then obviously hitting a rock within the clay. This is in Boston, I think Boston blue clay. So yeah, you see both parts of the assembly. So not rocket science, but you just need to have done it once to be able to do it. So typically those would be the ways that you'd sample. If you're using a rotary core, you drill down to some depth, you'd be taking samples. I didn't show, I thought there was someone in that previous, I won't go back to it. When the samples come out of that T-junction, the kind of house-fitting piece of white pipe with the T-junction, where the cuttings get flushed back up the hole, if you have a household strainer, you can grab a bunch of cuttings and see what you're going through, in addition to inform you of what you're going through from every time that you take a sample. Because if you're drilling with a rotary drill, with the tricones, every time you want to sample from the base of the hole, you have to pull out the whole drill string. Take a sample by driving a split spoon in or pushing down a thin-walled sampler, retrieving it, and then going back with the drill pipe and re-drilling with the drill bit. So it's kind of a laborious process. So rotary drilling is slower than tricone drilling, but you don't have to bring the bit up to the surface, because you can sample down below it, as I guess we talked about last time, right? Some of these samplers have an internal drill core holder, which is separate from the drill itself and can be taken up through the drill string without lifting the cutting head off the bottom of the hole, and then replaced to go the next 5 feet or 10 feet or 20 feet, whatever the length of the line is. So in line with getting advanced, with getting samples, I guess the other thing is that you'd like to get the most out of the hole as possible. So typically a borehole log would come along with that, and you, as an entry-level engineer or scientist, might be tasked with logging the things that come out of the hole. The driller just drills, and the driller helper just helps retrieve the material, but you're the person who decides what's going on. And so everything would typically go down in a log. This is a log, actually, I think, for Smithville. And it would maintain all the information you want to know about the site. So a lot gets put on here. So this obviously is a log, so it's with depth. Ground surface here, as you could imagine. In this leftmost column, along with the depth, the method of drilling, power auger, 150 millimeter diameter hollow stem auger. That goes down to the rock head level. And then after that, the drilling is with, or a casing is put in there, 100 millimeter diameter casing, socketed into the ground. And then after that, it's been drilled with air flush rotary, so air only, flushing it to begin with. And then it's had HQ rock core. HQ is the diameter of the core, the diameter of the drill bit. And is that right? 9.6 millimeter diameter hole, which has been advanced. Some description, no description in this part, because no samples are really recovered. This would be the hollow stem auger part. And if it wasn't sampled, there'd be no information. But once you get into the rock, and once you're coring, there'd be a full legend, if you like, for the core that is recovered. The core might be 100% of the length of the borehole, so every part of it would be covered. Not all of it might be retrieved, some of it might be destroyed or fall apart. And then some description by you of what the characteristics of that rock are. Limestone, sandstone, fractures, no fractures, staining as a sign of water flowing in it, etc. All kinds of things you could imagine. A kind of symbolic log to say what it was, soil. A logging along with the depth above the surface. So this is 1 foot, probably 1 meter actually. Yeah, this is Canadian. 1 meter penetration, 2 meters. So this would be the elevation relative to the surface. And so these would be the elevation below here. Whether you're taking samples, no samples in the hollow stem, but core, I guess RC must be rotary core. HQ is the diameter. I'm not sure what the other columns are. Yeah. If you are drilling with the split spoon, this is how many blows per foot. 0.3 meters is a foot. Metric magnitudes. None taken within the soil. And then for the core that is taken out, you can't see this very well, but this is the core that's recovered. This is 20, 40, 60, 80, 100%, I think, in that order. So this is how much core you recover, how much is solid, like in the Gobi Desert, one piece of core being 3 meters long, just amazing. RQD is the percentage of the core which is greater than 4 inches, 100 millimeters in Canada speak. How many fractures per meter? Obviously relevant, well, this is a hydrogeological core, it's a Smithfield site. How many fractures you have per meter in the system? And discontinuity fracture data. So dip would be the angle. So if you have core, you'd see whether the fracture is 90 degrees across it, along the length of it, which would be 90 degrees, 45 degrees, 0 degrees in terms of inclination. You can't get its orientation, right, because it's not really oriented. You can't get its azimuth for where that dip direction is. And some description of what might be on the core. Whether it's got iron staining, whether it has crystals as evidence of water going down, whether it has free product on it perhaps. I'm not sure you want to be touching it if that was the case. Additional testing that you might levy. So I've missed over this. So this is if you do an in situ test to measure hydraulic conductivity. And so what you typically, I'll skip that, what you typically might do in the hole is you'd put some casing in it. So in the legend over here, it mentioned that it has grouted steel casing that goes down at least to the rock, and then that would be grouted in place. And they don't do any pictures of it. They have a little cameo of it here. Why is it not showing everything? I guess I'm right up at the end of it. So this is a picture of the wellbore. This is the wellbore going down at larger diameter to the rock. This is the casing that, if it's cased going, perhaps not cased into the rock. This is where the casing that goes up to the surface being grouted in to give a good hydraulic connection, no flow in other words, between what's happening up here and what's going on down here. It looks like it has a piezometer tube go inside it, so a piece of 1-inch piping, just like you'd have in your house, PVC piping, that goes down into the bottom of the wellbore, is grouted by pouring concrete, a slurry of grout in here that seals off this tube from anything outside here. And at the bottom of this tube, you'll just have a number of hacksaw cuts in it to be able to let water into it. And this would allow water to rise up into this tube to whatever the water level would be in the groundwater. So this is your piezometer sample. Very rudimentary, but allows you to be able to blow water out of it to get a water quality sample as well as just the water level. And then what you can do in this, once you've everything settled down, is you just pour water down this tube to raise the water level by some amount, and then you plot as a function of time how that water table drops. So you raise it up to here, you get a certain height, you wait for 10 minutes, it goes down, you wait for 20 minutes, it goes down some more. The rate at which this goes down is some measure of the permeability or hydraulic conductivity. So typically in these completed holes, to get the most bang for your buck, you'd want to do an in situ permeability test to be able to measure that. And that's of course what this column is here, to plant that on the log. So if you did measure that, you just put the magnitudes on here. So this represents the record of everything that goes on in the hole, and this is what is the cameo of what you've seen in your Smithville assignments, what the stratigraphy looks like. And so, yeah, and other discussions. So pretty straightforward stuff. Again, once you've done this once, you've done it enough for the rest of your life. Getting the best bang for your buck. If you're paying for this hole to go in, you're going to use it for the most information. You're going to bag your samples, and you'll rack your core in core boxes so they're available to view afterwards by other people. Typically in some places they might have to go to a core repository with the province or with the state in a core shack, as we saw in Sweden, to be kept for posterity. They're very valuable. It's very valuable information because you spend a lot of money to get it. So tossing it away doesn't really make much sense. If you've got extra data from your hole by putting piezometers in it, this standpipe piezometer, you can also put dedicated piezometers in it. So you could imagine within the borehole, if you wanted to, you could just drop a pressure transducer in there. Pressure transducer would be the size of your finger. It would go down here. Oops, didn't need to do that. You would have electrical cables go up to the top. You'd backfill it with sand, which is permeable. The hole itself would be not cased, so it'd be intact. And so as the fluid pressures in here, so as the water table goes up and down over time, that's my representation of that, as the elevation goes up and down over time, then you'd measure that change in pressure. Right? That's why we do fluids, right? So we know if it's hydrostatic, then at time 1 it would look like this. If the water table rises to here, then we know at time 2 it would look like here. So measuring this pressure here and how it changes from P is equal to rho GH. H is the depth below the water table, then we can get what's happening from the water table. So this gives you pressure, but it doesn't allow you to access fluid. Standpipe piezometers that we just talked about allows you to be able to sample, even though it's an inch diameter pipe, inner diameter, you can still get liquid samples out of that, which will represent whatever the plume might be contributing. So different forms of piezometers. pneumatic ones, which is just a diaphragm, which is pushing against an anvil. The water pressure pushes against this diaphragm so that it closes the circuit between an inlet and outlet. If you apply a gas pressure here, which is equal to the pressure of the water acting here, you know that this pressure you're applying on the surface is the same as the groundwater pressure. And so as soon as it makes a continuous circuit with input and output, you know that you're at the same pressure underground. If you're in the vadose zone, the pressures you'll measure within the water will be less than atmospheric, a tensiometer, so-called tensiometer, and you can measure that. This is just a manometer, as you'd know, and this is a representation of a standpipe piezometer, just like the one we talked about here. And I think this is representing a pressure transducer is just a membrane pushed against by the water on the outside. It deflects, and you measure the deflection of this membrane with a little strain gauge, and you use that. That deflection then is calibrated with the pressure underground. So we'd like to know what water pressures might be. We might want to sample fluids. We might want to use these water pressures if we have information in a couple of different holes adjacent to each other. If we know the different levels, we could get some idea, if we knew the hydraulic conductivity, of what the groundwater velocity was. And so there are other exotic ways of doing that. This is using little finger heaters around a sensor. And if you have water flowing across a borehole, then the heated finger would transmit water from heat from this carried to an individual sensor in the middle, and so you could calculate the actual direction at which liquid is flowing. You can look at flow along a sampler by having a heater and a sensor. So if you pulse the heat here and you measure how long it takes for that heat pulse to get to this point here, it gives you some idea of the velocity in your wellbore. I guess we haven't talked about it. You can get little spinner logs, which you can drop down the borehole, and they'll spin like a little impeller. You put it down the borehole, it will measure a velocity of the water flowing past it. You pull it up the hole, it measures the reverse velocity, and if you subtract one from the other, it gives you the velocity of water that is naturally flowing up the wellbore. And so you might be interested in that because it might be coming into the bottom of your wellbore, going up here, and going up through a different aquifer. So all kinds of things that you could imagine. So these are quite exotic. Maybe more common today, you get borehole cameras. You drop a camera down the borehole, you run it along the full length, and you film all the way along. And a couple of things you can do. Really the main objective is to look at the structure on the borehole wall. You can pick out the location of fractures. Of course, you'll get fractures in the drill core as well. And so if you do it in a hole that's already been cored, you can say something about whether the ground truth, you can ground truth it for parts of the borehole which perhaps wasn't sampled. And I guess the other thing you can do is sometimes if you have a static camera and you see little pieces of silt or particles going past it, you can use that to calibrate how fast fluid might be flowing in the borehole to again give you some idea of what's going on, whether it's an aquifer that's flowing or whether it isn't. Lots of other different things. The kind of piezometers we just talked about are like these. These are standpipe piezometers. So the idea here is this is your empty drill hole that goes down to whatever depth. You put in that empty drill hole one of these pipes, piece of 1-inch PVC pipe that has slots cut in the end to let water in. You push it down to the very bottom of your hole, and then you dump down the borehole a whole bunch of sand, so it sits in a pad of sand. The sand comes up maybe a couple of feet to a natural level once you filled it. You know the diameter of a hole, you know the volume of sand, so you can estimate how much it will fill. And then once it's here, you pour down a slurry of bentonite, of clay, maybe of Portland cement to seal it. This acts as a plug. It has the standpipe going through it, so the water's isolated in this packet of permeable sand, but it's isolated from the rest of the borehole. And then you just tremie this sealant in here, and then the next time, the next borehole standpipe goes here, sit on the bottom. You fill this up with sand up to some height, and then you reseal it with another glob of a slurry of water and bentonite clay. Sometimes you just drop little pellets, maybe the size of the end of your little finger, down into the borehole. They're little compressed aspirin almost, right? With a varnish on them. They drop down to the bottom, the varnish dissolves, and then as they take on water, the bentonite as a swelling clay expands and seals the borehole by closing up all the holes. And then for each of these pipes, they all come up to a nest on the surface. You know which one accesses which zone, and so you can both measure the water levels in different zones along the borehole, or you can also flush it out by blowing nitrogen down it and flush out a water sample to be able to take a water quality sample on the surface. So this is obviously done in an open hole. There's no casing that's left in this hole, so the rig is off the hole, and you're just adding this piezometer nest. The other way to do it without a permanent installation is to use a straddle packer. So a straddle packer refers to the fact that it's straddling a zone. So this would be the zone in the borehole. So this is a tool that is dropped down the borehole. It has a central pipe, a mandrel, I guess a mandrel. And that pipe would hold apart two cylindrical cylinders, I guess, two typically aluminum cylinders, which have on top of them a sheathing of neoprene. And so this neoprene sheathing has gas lines attached to them, one going to the top one, nitrogen line to the surface, to a nitrogen tank to the bottom. They're not tight within the borehole because you can still get this tool down to the bottom. And then once you get it to the depth you want to, you just turn on the tap up here, put nitrogen into each of these packers. They expand like a balloon against the borehole, and they seal it from up, and they seal it against down. So now you have a straddle packer zone, which is this, which is isolated from the borehole above and the borehole below. It doesn't necessarily have to be at the bottom. It could be retracted along the borehole. And then you do this to do exactly this slug test that we talked about. I guess I didn't call it a slug test, but the idea that you put water into the hole at some time, and then you allow it to flow out into the formation, and you just record its elevation at different times. The elevation of this with time gives you an idea of how permeable the material is. So you can convert this into hydraulic conductivity. The only difference from doing it here is that this is doing it in a place where every time you do this experiment, it's exactly the same location in the borehole. If you do it with a straddle packer, then you can do it at the bottom of the borehole, and then you can work your way, if you wanted to, all the way up to the borehole to places of interest that you might be in to be able to make that same measurement. You can also come back and you can re-enter it and go back to the bottom and just repeat it. So this is the red line is where you'd fill it up to some level within this line. You'd overfill it to some higher level, and then you'd let this flow out of this zone into the formation. And in doing that, there's a complementary, every volume that goes out here comes down here, so you know exactly what this volumetric flow rate into the formation is, and so you can calculate permeability. When you've got the measurement, you deflate the packers, you winch it up the borehole to where you want to go, and then you inflate these again. It's a very standard way of doing that. Not sure what else. Must have some pictures. It's picture time. Is that the movie? Yeah, these are, yeah, I must have pictures. That's something else, I don't know. Gone through Switzerland. I didn't do a very good job of finding that in advance. That's exactly it. So that's it, nothing more than that. So these are the nitrogen lines, or it could be compressed air for that matter. It doesn't need to be nitrogen. Nitrogen is nice and inert. Air would be just as good. This is a steel cylinder on which this sheath of neoprene, just like a wet suit material, is put on. It is able to be inflated by each of these lines independently. One of these lines will go through this top packer into the bottom packer. There'll be a spacer between it. That spacer could be 1 meter long, or 2 meters long, or 6 inches long, and they'll be joined. I thought the previous one was that. Perhaps I don't have a picture of the joint. Yeah, you can imagine it. They're joined together and separated by some amount to measure this. So taking measurements like that. I'll go back. I didn't want to go quick. These are all underground research labs. These samples are taking fluid pressures in packers. This, I don't know where this is. Is it Mizunami? This is in Korea, in Daejeon, Korea, in an underground site for exploring the feasibility of storing radioactive waste underground. So just a tunnel, I think, yes, this tunnel. Just an experimental tunnel that happens to be in a town in Korea with all the instrumentation, measuring fluid pressures. This is Mizunami in granite. These guys are taking hypodermic samples of tracers introduced in a borehole, arriving in another borehole, and looking at the arrival time of those to understand the flow regime. This is in the main island of Japan, just south of Tokyo. This is in Monterrey, an experimental tunnel underground research lab in the French part of Switzerland, in the Jura. Rolling countryside near Geneva, the French-speaking part of Switzerland, not the central German part, and not the southeastern Italian part. This is just coring into the wall to get a sample. This is where it is, in Saint-Ursanne. A bunch of drifts to be able to do experiments in them with drill holes placed in them to run different injection experiments. Don't know what this is. Just the noise of the thing. Borehole breakouts. So stresses on these make these fracture in shear. And so these are indicators of where the stresses are applying. They're used as indicators of that. A cleaned off surface to be able to look at fractures, Zurich. An experiment at the end of one of these little tunnels to look at, some of these experiments were looking at how well bentonite sealed up heated containers and stopping their products escape by going along a little tunnel. This kind of idea, this is a model of exactly what it was, rather than the actual thing, but it is underground. So fuel rods in a container, placed within a canister, placed within bentonite underground. The idea being that the bentonite, if these canisters break, then the bentonite is highly sorbing, so it soaks up radionuclides and doesn't really allow water to flow through it. Actually, the actual experiment in this particular case. Fractures. A little trolley to lie on and pull you into the tunnel. This is probably a meter and a half, I would say. St. Barbara, the patron saint of miners. Another underground research lab in Switzerland. This is in Grimsel, in granite. Boreholes and some experiments done underground. A super big packer. You know, we talked about straddle packers straddling in a borehole to isolate a central portion. This is a packer that straddles a fault. So a fault is a kind of broken zone within the rock, which is present coming down vertically. It's the full length of this width, which is maybe 4 meters, perhaps 15 feet or so, something like that. And so this is a steel casing with a neoprene packer on the outside, which is inflated against the wall to be able to do experiments in this big fault to see what the hydrogeology of this natural feature is. So, again, a bunch of experiments underground under those same conditions. Seen that before. Measurements of pore pressures along boreholes away from this wall. Big crystals in a geode, natural geode, on the surface. It's that Grimsel site is an actual dam. And I guess this is the one I was looking for. So this is a straddle packer. So on the right-hand side of packer, left-hand side of packer, a choice of the height, length of the zone. This is water introduced along the axis inside this straddle packer to be able to run a slug test, Lugeon test. This is the nitrogen supply to inflate the lower packer. And this is, these are probably 4 inches in diameter. This is probably 18 inches separation. You can change the separation of the straddle if you want to sample a bigger zone. And I guess the only interesting thing about this location was it was an experimental site for underground science, but it was also a decommissioned French ballistic missile silo base. So I don't know if it has in the southern French Alps. Rustrel is what it's called, LSBB. It's very close to Saint-Cyr-sur-Mer. Are you playing games on that thing? Busted. I know you're not paying attention, any of you, so it's not picking on you. So, beautiful countryside in the southern Alps, and that's probably it. So, as we go through this, so we said we'd talk about a couple of things today. One was to talk about sampling and methods of sampling. We've done that. The second, 1.5, was talking about getting the best bang for your buck to be able to put instrumentation in if you want to use it. And the other one was, I can't remember what I referred to it, but is in situ sampling without destroying things, so-called direct push methods. And direct push methods are exactly what you might suspect they are. And the idea is that instead of drilling, which is a laborious process in soil, what you can do is you can just push from the bottom of a van into the ground a probe, which by its mere act of being pushed into the ground, you might be able to record something about what it's going through. What's the time? Yes, I'm just trying to see. Oh, we're in good shape. In pushing into the ground, it merely measures something which is of use in interpreting exactly what you're going through. And so it's a bit like a cross between direct investigation, where you go into the material itself, and indirect investigation, where you use geophysics, where you measure some parameter which is a proxy for the material that you're going through. And so here you push this through the ground, and it would be typically, it's a 10 centimeters squared cross-sectional area. So the circular, if you look at this probe, bless you, end on, then it's about 5 centimeters diameter. Is that? This is 10 centimeters squared. This end view of this is 10 centimeters squared. So it's of the order of 1.5 inches. Is that right? That would be 4 4s is 16, so that would be 16 centimeters squared. So it's less than 1.5 inches. It has a 60-degree cone on it. It is attached to the surface by these rods, which go all to the surface, and it's pushed into the ground typically at 2 centimeters a second, standard rate. And 3 things are measured. Around this collar is a piece of filter which allows you to measure the pore pressure as it goes down as it follows down into here. So as you measure, as this is pushed into the ground, you can measure it as at every elevation that it passes, the exact magnitude of tip resistance. In other words, how much force is applied on this tip. Doesn't sound very hydrological, but it is. You can measure how much friction is applied to the side of this sleeve. So if you have a little load cell here that measures the force here, then if you have a load cell here that measures the force here, the difference between these will be the magnitude of the tip resistance, and the difference will be the sleeve resistance, the friction here. So you measure friction, just like friction in a pipe, but it's friction of the solid against this thing that's going down at 2 centimeters a second. You measure the force you have to apply to push this into the ground at this portion here. You measure the fluid pressure that you generate, and so at any particular depth you get an instant sample of each of those three metrics. You might measure electrical resistivity between sensors on here as well, but the three main ones are the ones that are on the left-hand side. You keep on going until you can't go any further, or as far as you want to go, and then you use these records of a value of tip resistance, friction, and pore pressure at every depth as a combination of parameters that is some proxy for the particular behavior that you can see. So if you've done these experiments in enough places, and you've also maybe drilled alongside and run split spoon tests and taken Shelby tube samples, then you can correlate the magnitudes of the parameters you're measuring. The cone bearing is the tip resistance. The friction ratio is the sleeve friction. And so if you measure these magnitudes next to boreholes where you've actually sampled them and classified them as clays or silts or sands or gravels, then you might be able to figure out exactly what magnitude of friction ratio and end bearing was indicative of a particular type of soil. And that's exactly what this is. These numbers, 1, 2, 3, 4, 5, 6, which measure a particular magnitude of friction ratio and end bearing, which would represent the magnitude you'd measure as tip resistance and friction ratio here. You'd have those magnitudes. So if you can correlate those with something else that's been measured independently, and if these charts are kind of standard for any site you go to, you can say, if you know what the magnitudes of these are, that it's a, whatever it is, what number 3 is. 3 is a clay. That's all. If you can also do the same thing for the pore fluid pressure that's developed, and how that magnitude of pore pressure ends up being with the same value of end bearing, then that also gives you some indicator. Hopefully every time you end up with a point that ends up in one of these divisions, it's the same division, because it's supposed to be. You could imagine that it might not, but anyway. So anyway, you can use direct push technology to be able to do that. And do you need to say, yeah, fine. Let's look at some of these. What else do I have here? No, the other one. So France, the Jura. Perhaps it's earlier on. Don't mean to give you whiplash, but yeah, okay. Actually, you get the idea here. This picture isn't a bad one. It was a horrible picture, but it shows the idea. And so this is the idea. These come on trucks. Sometimes they're interior, sometimes they're exterior. They have stabilizers to be able to lift the wheels off the ground and give a firm foundation. And then inside the vehicle, this is the rod that's being pushed into the ground through the floor, a hole in the floor. These are 2 hydraulic rams that grab onto the rod at the top and grip it. They go down at 2 centimeters a second to be able to push this directly into the ground. Quite an old picture. It's an old computer. And then here, this is the cable that's measuring the end bearing stress, the sleeve friction from load cells, and the pore pressures from a transducer, and it transmits it up to the surface. And actually it's already pre-wound. It goes through a whole bunch of these typically 3-foot or 5-foot rods, which you just add another one onto the top here. You screw it in the same kind of fitting that we saw in the drill rods. This plinth comes back up, grabs the top, and then continues going down at 2 centimeters a second. Add another rod, get down to the bottom of the travel, and then you add it. So that's exactly what's going on. So here you see that in action. This is in Izmit or Izmir, I can never remember which one. One of them had a big earthquake in the early 2000s, and a load of buildings got destroyed. It's in Turkey. I think it was the Kocaeli earthquake. This is Istanbul, this is Bosphorus, Black Sea, Sevastopol, Ukraine, or Russia, depending on your nationality perhaps. And this was an earthquake, probably killed 20,000 people, I think. And so the big question here is that it killed people by liquefying sand, which instead of being solid became a slurry, and buildings would fall over and sink in it, and septic tanks would pop out because they're buoyant in this slurry. So this was to investigate, kind of understand the mechanics of liquefaction to be able to see how to solve that problem so buildings don't liquefy. And the Anatolian fault must run across here. It's the same one that kicked off in Syria in February 2 years ago, I think. So this little doodad is yeah, okay, you see something. So this is the little instrument that's going to push these things into the ground. These are the individual rods, which are having the data cable threaded through them so that they can be mounted and then added to each other. Better, maybe a clearer picture there. This is the rig. This is going to physically push it into the ground. It comes on tracks. You just steer it from a box, like you see the guys driving these overhead booms on campus to get to them to where they want to get. So yeah, this is just putting the cable through here on the length. This is the tip. This is the 60-degree cone. This is the porous pressure measuring component. There's a load cell back here. There's a load cell here. This is a friction sieve. This is pre-soaked and saturated in silicone oil, so you don't get any bubbles in it. Can you guess what this is? It's a condom. It's keeping this all in to be able to keep it saturated. And then physically it's just pushed into the ground and this will get ripped off. I don't know if this is it. This is... Not great photography, but you can start to get the picture. This is probably a better one. Actually, it's not. So this is it. So it goes on the stage, it gets put on the ground. This is the thing that clamps the top, and it physically pushes it into the ground while it's going down at 2 centimeters a second. It's probably a meter long, so it must take 50 seconds to travel to the base. In that time, you screw on the next one, and then as soon as it gets to the base, this retreats rapidly up here, grabs the next one, and pushes it down. Must be some pictures, yeah. So this is loading the rod into this. These are all the spare ones loaded here. I'm guessing it might be loud. Don't pick your pants when other people are watching. You might be right on the money. And that's 2 centimeters a second. So I guess these aren't the ones that are going to follow it down. The ones that are going to follow it down are the ones on the ground with the green data cable going through it. So, poor guy. And we're back where we are. Is that it? It must be it because I hear movement. Did the game finish? No, the game's still going on. Where's that? This point? Are we finished? Yeah, we're finished. So that's it. So this was our penultimate class. Next time we'll talk about indirect methods. So now you have this good picture of what happens exactly on this long line, which might be only the size of your fist all the way down. If you've sampled it, you know exactly what's there. If you've direct push sampled it, you might have a good idea of what's there as well. But if you want to expand that out to know what's over the other 5 acres of your site, you might want to be able to fill in between those boreholes. And so next time we'll talk about geophysics, which uses proxies for the properties that we like: clay, limestone, quartz, etc., sandstone, to be able to link up with the ground truth from the boreholes and to fill in the gap in between. So we'll talk about that next time.